this lesson. So in this lesson, we're going to go through the third technique of numerical integration, and that is the Romberg integration. Now, let's actually recap what is the purpose of numerical integration. So numerical integration, the purpose of it is to numerically find the area under the curve, or to estimate it, to not use or resort to integration rules. And we have started with the simplest of techniques, and that was the trapezoidal rule. And the trapezoidal rule used a first order polynomial, which is, we have the linear function here, and we found out getting the area under a linear function gives us a shape of a trapezoid, which is where this rule gets its name. And we also examined that maybe by the use of one trapezoid, maybe the approximation is not accurate enough. So what should we do? One way to do it, we examined using multiple application trapezoidal rule, or using multiple trapezoids under that area. In this case, we examined 2 trapezoids, and in this case, we examined 3 trapezoids. But we also examined another way of getting a more accurate approximation, which is, instead of using a first order polynomial, we started using a second order polynomial, which made us get introduced to Simpson's 1/3 rule. And this actually uses a special type of polynomial, which is called a Newton interpolating polynomial. And we find that that gave us a more accurate approximation simply because it's a higher order polynomial. Also, we found out that even if this is not a good approximation, we can use a multiple application Simpson. So we can actually use 2 different applications here. We have one application here in the green and another application in the yellow. So up to this point, the most accurate method that we know is a multiple application Simpson's 1/3 rule. It turns out that we actually have a technique that is actually more superior to the Simpson's 1/3 rule, which is called the Romberg integration, which is dependent entirely on the trapezoidal rule. So how does the Romberg integration actually work? What the Romberg integration does, it takes, say, an approximation for a trapezoid here. So say, for instance, we have this function, and I want to approximate it between 0 and 1 using one trapezoid. And also, I want to approximate the same area using a multiple application trapezoid using 2 trapezoids here. So what the Romberg integration does, it takes this approximation and this approximation and combines it in a unique way to get an even better approximation that is superior to all the techniques that we've learned up to this point. But there's one criteria when it comes to this technique, that the 2 approximations that you're going to be combining, one has to have the half of the step size of the other. Meaning, this is one trapezoid, which has one step size to 2 trapezoid. So when you're combining, I can only combine 2 and 1. And if I'm going to combine something else, I'm going to have to combine, say, 4 and 2, then combine 8 and 4, 16 and 8, 32 and 16, and so on. So with the use of the Romberg integration, if you want to combine 2 estimates to get an even better estimate, the one has to be half the step size of the other. Okay, so let's actually examine the simplest form of the Romberg integration, which is basically combining an approximation using one trapezoid and an approximation using 2 trapezoids. So this is the simplest version of the Romberg integration, which is basically, I'm going to take the more accurate one, which is a 2 trapezoid, and I'm going to give it a weight of 4/3. And I'm going to take the less accurate, I'm going to give it a weight of -1/3. Now, if you notice, the addition of these 2 will add up to 1. And you're going to find that here I give this a designation of I21, and this is the designation of I11, and the new one has a designation of I12. Now, these subscripts I will explain in just a moment. Now, what if I want to get even a better approximation than this I12? Well, instead of combining the trapezoidal that is an approximation of 2 with an approximation of 1, I can combine approximation of 4 trapezoids with an approximation of 2 trapezoids, which will give us this expression. Now, we still have the same weights, 4 divided by 3, -1 divided by 3, and also this is I31, which corresponds with the more accurate one here, and the I21, which corresponds with the less accurate of the 2. Now, we can actually create a general equation that can actually encompass all different types of combination of the Romberg integration, because right now I have two equations that define combining 2 with 1 and 4 with 2. So I want an equation that can actually not only combine different approximations of the trapezoid, but can do different levels of integration. Now, what do I mean by a different level of integration? When we did this trapezoid, the 4, the 2, the 1, that was the first level of integration. These I12 and this I22, these were the second level of integration, which actually makes sense where this 2 comes from. This 2, which here will be defined as k, will indicate the level of integration. Here, we have 1 here, 1 here, 1 here, and 1 here, implies that this is our first level of integration. Now, the reason we need a generalized equation, because right now with this example, I'm showing you the first level of integration and the second level of integration, but you can go as deep as you need to be to get the estimate that you need. You can go to a third level, a fourth, a fifth, and a sixth level. So let's actually examine how this would work. So if we look at this generalized equation, J implies the accuracy of your technique. So J1 is going to be less accurate than J2 and 3 and 4. And we can actually see this here. This is J, so we have 1, and here is 2, which the 1 indicates the least accurate one, and the 2 indicates the most accurate one of the 2 here. And also we can find that here 3, J equal 3, implies the third accurate approximation that we have of these 3. Now K implies the level of integration, and I told you this is the first level of integration, and after combining for the first time, this is the second level, and if we combine again will be the third level, combine again will be the fourth level, and so on. So let's actually see how this equation would reduce to at least these 2 for now. So if J in this case is 1 and 2, so if J is 1 and 2, if J is 1 and K is 2, if K is 2, that's 2 minus 1, so that's 4, and this is 4 minus 1, that's 3, so that's 4 divided by 3, so we have this weight here, and that's going to be negative 1 divided by 3, so we created this weight here, and we have J plus 1, so that's 2 and 1, and also we have 1 and 1 here. So we find that when we put J as 1 and K as 2 for the second level, this equation reduced to this equation here. So let's actually see if this is going to also reduce to this one. So if I is 2 and K is 2, so 2, 2, we're going to find that we still retain the same weights, which is 4 divided by 3 and negative 1 divided by 3. But the only thing that really changes here is here the J, since the J now is 2, this becomes a 3 and this becomes a 2. So let's actually see one realization here, that when you're dealing with J and K, you can actually notice that this is a notation of a matrix, right? So J indicates the rows and K indicates the columns. So let's actually see how this equation would expand into a matrix, right? So this is I11, which is basically the approximation of one trapezoid here. This is I21, which is approximation using 2 trapezoids. This is I31, which is an approximation using 4 trapezoids. And this is I41, which is an approximation using 8 trapezoids. And remember, we have to go with a multiple, right? 1, 2, 4, 8, 16, and so on. Which is why the I31 corresponds with 4 and the I41 corresponds with 8. Now, if I combine the I11 and I21, like we've seen here, I can get the I12. And if I combine the I31, which I have here, the I21 I have here, I have the I22. And if I combine the one that has the 8, the approximation for using 8 trapezoids, and the approximation using 4 trapezoids, I will get the I32. Now, here is where I have a new concept to share with you. From all I have showed you here, I've showed you the first level of integration, and I've showed you the second level of integration. But actually, we can go to a third and even a fourth level of integration, right? because here we have combined the estimates of the trapezoid to get these combined estimates, right? But it turns out we can actually combine these to get even better estimates, right? So whatever we created from these equations, we can combine them again to get an even better approximation. So I can take this I12 and this I22 and I can combine them to be I13. So I created my third level of integration now. And I can also take the I32 and the I22 and combine them into an even better approximation, I23. And I can even do this even one more time. Like here, this has been a combination of these, so I can combine these again using the equation that I have over here to get even a much better approximation, which is going to be our fourth level of integration. And you can see that because of this type of combining, this technique becomes far more superior than any other technique that you've used thus far. And I know this technique, as you have seen, is not very intuitive technique, but it's a very powerful technique. So let's actually briefly recap what we learned in this lesson. We've learned the third technique that so far, which is the Romberg integration, and is based entirely under trapezoidal rule, which basically combines two approximations of the trapezoid to a better approximation. One criteria is one approximation has to be half the step size of the other, right? And from this type of equation, we have created a general equation for the Romberg, because this is all you need to know when it comes to the Romberg, this equation, as this is all you need to know for the Simpsons, and this is also all you need to know for the trapezoid. So this technique is encompassed within this equation. And we found out that we can actually go to as many levels of integrations as we need. In this case, we have went as far as 4 levels of integration. Now, what if I want to go to a 5th level of integration? Well, to go to a 5th level of integration, if you remember, this is approximation with 8 trapezoids. If I get an approximation with 16, I can combine these two to get the I42 here. Then I'll combine these two to get the I33 here. Then combine these two to get the I24 here, and to combine these two to get the I15 here. Now, in a later lesson, I'm going to show you how this can easily be done using a code. And from this point, you can just define what type of error that you need, and the computer or the code will decide how far of a level of integration it needs to go. Well, this is it for this lesson, and I will see you in the next lesson.